All right, welcome back. Module 8, Part 2. This section we're going to look at a little bit of general purpose input-output review. We're also going to kind of try to bridge some gaps of some of the stuff we saw in our GPIO lesson with the line sensors and how that's all working in memory and how our inputs and outputs correspond to memory. So this first graphic here just shows all of the different ports that are connected to the MSP432 launchpad and give us access to the MSP432. So we see each of these ports aren't lined up very well in regards to just numerical order. But if you take a look, for example, you got your 0, 1, 2, 3, 4, 5, 6, and 7. So that's all of port 9 right there. But the way these ports are accessible to us as programmers or in this embedded system is through memory. So for example, if we take a look at port 1 and port 2, there's a number of different, I call them registers, they're really just memory address locations. But for example, port 1 in, when we use this kind of nomenclature, what we're really doing is this is built in for us as a memory address. And that memory address that you can see here is located, at 400.4C00. And if we go back up to our memory map here, we can see that falls in within our I/O ports. And so each of these different memory addresses, each port has a number of different memory labels that go with them, input, output, direction, remember our resistor, pull up, pull down, our select bits for GPIO, and what's going to happen is when we access one of these ports, just like this, port 1 in, we're actually accessing the 8 bits of data that are coming off. So now this bit here is port 1, 0, so that's that pin port 1, 0, port 1, 1, port 1, 2, etc., etc. So say I have an LED that's connected to port 1, 0, and I have a switch that's connected to port 1, 1. So if I want to read the data that's, so let's call this switch because it's an input. This will be our LED. And so if I want to read the data that's our switch, is it pressed, is it not, I have to read and select this one bit of information. So that's why when we're looking at things, we're doing, port 1 in, ANDing that with 0x02, because 0x02 represents, 0, sorry, let's do this in binary, 1, 2, 3, 4, 1, 2. And if I take this whole piece of data right here and I AND it with this, my input now, I'm just selecting this one bit. All right, so that's why we have to select that one bit there, because we're trying to get that as an input. Now let's take a look at the output on the other side, our LED. So P1 out, we're going to set that equal to P1 out. And this is where it comes in, where we have to get the previous information sometimes and OR it or with our new information. But let's just say we want to just turn on that one LED right now, and that's all our function does. So if we just want to turn on that one LED, then we can just OR this with 0x01, and what that's going to do is all this other data is going to stay the same because we're ORing that with 0. So this would be ORing it with just this here. So if we OR anything, so let's OR this now. What we're going to get is we're going to get a 1 here, and then X is all here. X's being whatever was previously there. So all good. We are happy. We've ORed it, and it's good to go. Now the difference is if we want to clear it, that's going to require us to, if we want to turn off the LED, then we can come in and do our 0x01 just like that. I like this format because now I know I'm trying to change the 0 bit of that output, and I know that because of the 0x01 hexadecimal, but you could theoretically just OR it with a bunch of, or AND it with a bunch of 1s and a 0, but that's not as meaningful as using the opposite of the not of 0x01. And so now if we take a look at that, what we're doing, we're ANDing with things we don't know that's in here because we don't know what the output was previously, but we do know is that's going to be a 0 and this is going to be whatever the whatever was in there previously. And then we write that to memory, and that's where this P1 out, because we're going to push that right back into those registers. Now if we don't know if we're going to switch between clearing and setting, that's where it really becomes important to clear that memory first, and then clear the bit of interest first, and then OR it with our new information, and that's what's going to allow us to do that. And we really just need to do that if we are using a variable. So if some other function is going to turn on or off something else. All right, so that's the memory address, and that's kind of how when we are messing around with these select bits and these directions and outputs and inputs, each pin has their own input, output, direction, select, but it's in a port kind of method that allows us to access it all at once. And we can figure out where those ports are in memory by using this piece of our data sheet, MSP432 data sheet. So if I want to specifically, get the direction memory address of port 2, I know it's at 0x4000.4c, and then it has an offset of 0.5. So what that means is that the port 2 direction is located at 0x4000.4c05. So we just added 0.5. And that's, we're going to use that in the assembly code because we're going to be using these addresses to write to specific port bits. So I just want to give you guys that little piece of information so you know where to go. All right. So I pulled in the function selection. So every port and every bit in that port, so port pin 10 has a direction, a select, and a select 0, select 1. And so if that specific pin was a 0, 0, then it's a general purpose input output. So we have to clear those bits. Same with our direction. If it's a 0, it's an input. If it's a 1, it's an output. And then if it's an input, we can activate our register pull up or pull down. So the 1 there activates it, and then an output, since it's an input, right, it has no output, we can use that output bit to determine if it's a pull down or pull up. And what's happening, and I wanted to kind of go in and look at these D flip-flops because this is a great connection back to 281, is that each of these ports has these flip-flops and buffers that look just like this. And depending on what our different flags are, so if our P direction flag is a 1 or a 0, so say it's a 0, that we already know that's going to be an input, but what we've done here is we have a 0 here, it turns off this buffer, and information is not going out towards the port, but information is coming in. That makes, hopefully that is clear there. And then if we do that on the opposite side and we turn on our, so if our direction is a 1, then we're putting 1 out. That's going to activate our output portion, but also we also have a feedback that's going to give us the previous information. And so that's when we're doing things like over here where we have our P1 out and we're ANDing that with something else. That allows us to get that information with this this flip-flop here to get our previous information. Remember, there's a clock cycle between these flip-flops. Hopefully you guys remember that from 281. And so this is giving us our previous output. And then when we do go to write, we're going to send the next information out to the bit. But we're able to read from the output. And that's not using this because that's a whole separate piece of logic. But this allows us to read from that output, or really what we're seeing is what it was the previous output, so that we know what the values are supposed to be, and we can maintain, say, port 4, 0 through 4, we don't care, we're not changing those, but we do want to keep those to be whatever they were before, and then we're going to change maybe port 5. So here's the C code examples that we've seen before. So, we are going to set port 4.2 and 4.4 as GPIO inputs with pull-up resistors, and then we're going to read the data. Okay, so we know GPIO, we have to clear the select 0 and select 1. We're going to clear, and we know, so if I have the 8 bits, right, so port 4.7, 6, 5, 4, 3, 2, 1, 0. And if I want this, and this value, that's going to be 0x1c. And that's why all of these are using 0x1c, because those are the ports we're messing with. So we clear just those. We're not clearing any of the others, because when we do this, right, we're actually clearing only those 3 bits. And then we're going to set our direction as an input. And if we go back up here, direction needs to be 0, so we're clearing. Then we are using, we're going to have a pull-up resistor, so we're going to enable that resistor. And then since it's an input, we use the output to determine if it's a pull down or pull up. We said pull up, so we're going to set that value. Again, remember, ORing with a 1 is setting, ANDing with a 0 is clearing. And then the last thing we need to do is read from that port. And we just take that comes in, so that is our values here, but we're going to shift those to the right too, because otherwise we're going to get, say all 3 of these were on, instead of getting just 3 values, we're going to get 0x1c, which would be all 8. And so we just shift those to the right too, so that they're in our top least significant 3 bits, and now that represents the values from port 4.2 to 4.4, and we can put that in result. We saw that in when we were reading from the line sensors, when we only wanted to read the center 2, we shifted those right. All right, now 2 more examples here. Well, let's go real quick, remind the 4 steps. So 4 steps for input. So step 1, set GPIO. Step 2, set direction. The register is optional, but we are using it this time. Step 3, which is read. So right here is where we're reading. So this is 3, 2, 1. And step 4 is select the bits of interest, which is what we're doing here. So we're selecting the 3 bits, 2 through 4, and then we're shifting those right to sit them in our key 0, 1, and 2. All right, so that's our 4 steps for reading. Now, I'll just move that so it's kind of up our way. Of course, never works quite how you want it to. Undo. All right, whatever. Just gonna move on. All right, so the next example. There we go. All right, the next example configures port 4.3 as GPIO output and initialize to off. All right, so first step here, we're going to, again, GPIO, and we're clearing. Then our output needs to be a 1, so setting direction, we're setting that to a 1. And then our, so then we set our direction, again, output, and then we will read from that output, or sorry, set that output initialize to off. So we're writing to the output. So, and then we're turning it off, so that's a 0. And we're only turning off that 1 bit, and so we can do P4 out, clearing that 1 bit. So this example we don't have to read first. So I know in the first GPIO lesson, or the first step, second step, step 3 was clear or read, which reading was the P4 out. Step 4 was clear the bits of interest, which would have been P4 out. All right, so, and then clear 0x08. 5 then is to either set or clear depending on what our input was. So that's setting clears when we take all of this now and we OR it with our new value. All right, so those are our 5 steps, and then 6, obviously, write it to P4 out equals all of that above it. Okay, so those were our 6 steps before. So in this first example, we know we are clearing, we are initializing to off, so we don't have to do all of that. We can just turn it to 0. We know we're not changing any of the other bits, so that's still friendly. We could do the same thing if we knew we were going to set it. But where we have to do these additional steps is when we don't know what the new value is going to be. So for this example, let me pull up my notes. So for this example here, we are taking input in from some other source, and we're going to write that to port 4.3. And since we don't know what that value is going to be, if that value was a 0, and and like we saw in the previous, if we don't know what that value is, that's where we have to bring in this additional steps. We want that data to say it's just a 1 or a 0 because it's going to port 4.3. So it's going to be 0x01 or 0x00. I'm going to have to shift that left 3 so that it goes to port 4.3. So if it's a 1, that would then be 0001. And if it's a 0, obviously it doesn't matter, but it could be a 1. And we shift it left, then we OR it, and we're good to go. But if it was a 0, we'd have to clear it first and then OR it with a 0. So that's why we have to do that additional step. And we can do all of these exact same things in assembly using these 4 different logical operations. Obviously, you have to load it into memory, all of those things. And in the code for the LEDs.asm, which you'll see in the lab. There's examples of all of this above it before you have to do it. So look at those examples and then just kind of think about the logic. Are you trying to clear, set, toggle, or select? And then you'll know which of the assembly codes to use, or assembly instructions. All right, so I wanted to get into just a little bit of some stuff with the what we're going to implement in the lab. So a switch obviously allows us to, when it's not pressed, it's an open. When it's pressed, it's a closed. So if we have, depending on how this is set up, obviously it's going to be a 0 or a 1, one way or the other. The way this switch is set up, and you can see it here, is nodes 1 and 2 are connected, 3 or 4 are connected, and then the switch goes in between those. So pay close attention to that when you're wiring up your circuit, because that's going to mess you up. Here we go with our positive logic, and that's active high, and uses a pull down resistor. Okay, so what that means is we have 3.3 volts coming into the circuit, and when the button is pressed, it's going to be 3.3 volts, or when the button's pressed, it's going to be high. When the button is not pressed, it's 0 volts, and it is low. So that is what defines active high. It's when the active state, is it a high voltage or low voltage? So in that case, this is negative logic, active low, and uses a pull-up resistor. We're going to actually have examples of this in the lab. So this one here, when the button is pressed, it's a 0, right? Because ground, everything goes down there. When the button's not pressed, it is high, 3.3. So low, active low, button's pressed, it's a 0. Active high, button's pressed, it's 3.3 volts. The key thing to note with the LED is there is a positive and negative side to the LED. Longer side is positive, shorter side is negative. Often there's a flat portion as well. And so what we're going to implement in the lab next time is we're going to have the buttons, our inputs, they're going to do something. We're going to have all of our logic and software, and we're going to see the output in the LEDs. All right, we'll see you next time.